definitely go to that GitHub repo. There's a Docker file that will make your life a lot easier. You just download it. It's fairly large, but it will run and everything will be happy and fine. But there's also requirement text, and you don't necessarily need to use the Docker file. But it makes sense for you guys to get started on that now because it might take a little bit of time to download.
And just to clarify, you can just do the Docker run and then the image name, and then that should start it for you. And I think that's on the next slide, in fact. Where are we? Yeah? Cool. So I'm going to go in present mode. Yeah, so if you guys have already got Docker installed, then you should just be able to run this first line, and that's going to open up a Jupyter notebook for you, as well as download the image. So just because it is quite large, I think we should go ahead and do that first, such that we can go through some of the slides while it's preparing. So that would be great if you could you could just run this in the command line if you already have Docker installed. And that should get the process, kick it off. Cool. And we'll go back.
Yes.
So just to introduce ourselves, my name is Matthew Moocarme. I'm a senior data scientist at Viacom, where I help Viacom bring value to all of our social media campaigns and in the reporting, tracking, and planning phase. I enjoy that. I come from a background in physics, where I was classically trained as a physicist. Where I got my Ph.D. last year from CUNY Grad Center.
And I'm Ben Batorsky. I'm a data scientist at ThriveHive. ThriveHive we do, and that's sort of the data set that we're going to be using is kind of derived from some ThriveHive data. We provide managed marketing services and platform services to small and mid-sized businesses. So it's a really interesting set of data. We have data from web traffic. We have data from our users' activity, their customers' activity. So it's a really interesting set of problems, an interesting population that we're dealing with that may have very little sophistication in digital marketing, and we sort of help give them guidance, and that's sort of the initiative that we're going to be talking about today is sort of out of doing that guidance for customers and for our internal teams. I put way too much contact type information in there, so feel free to check out the ThriveHive Tech blog or me on Twitter, GitHub. He also has a GitHub, but he's not going to put it on the slides.
I'll add it in there so that we can share around this slide, so that you can, because that's where the repo for this project is.
Yeah, and this is
it's also up there.
Yeah.
So we'll go ahead and go back to this slide just to make sure everyone is on the same page. Is there anyone that's having trouble getting Docker up and running or has any trouble? Because I think now would be a good time to sort this out. Otherwise, I found that in these kind of tutorials, partnering with your fellow neighbor is a great way to learn from each other, as well as if you're having issues, ask them as well. Yeah, so we'll pause for 5 minutes and then give everyone an opportunity to at least get things running, and we can go around the room and debug some issues if there are any. So yeah, if you have any issues or anything, please raise your hand, and either Ben or I will come around and try and resolve them.
Can you just look up Windows install Docker? Just Google that. Yeah, basically it's. I don't Exactly, and it'll give you like a URL to access that'll have the Jupyter notebook, and it'll have everything. So, yeah, the Docker will take a little bit of time. Yeah, definitely just interrupt us if there's. Yeah. So some people might be having trouble with that link for Windows. It's basically, we were just trying to give you a link for if you have Windows and you want to install Docker, just Google Windows Docker install, and that'll give you instructions as well.
With Windows, that is
that the only way?
If you just have Windows.
Yeah, if anybody has problems with Windows, it might make sense to use the requirement text, and if people need to know how to do that, raise your hand and we can try and help you with that. Otherwise, share with your neighbor. Is it Windows issues?
I actually tried to but this is my work computer, so I'm going through the work server.
Okay. So it's just taking a bit of time.
Well, I'm not sure exactly where to start.
So if you want to use the requirement text, if that's the way you want to run it, then do you know how to use requirement text files with that?
Yeah, that's why you leave
Because if you do have Docker installed, you don't have Docker installed.
No, I don't.
It takes a while.
Well, so if you do pip install, I think it's R in the requirement text, it should install all those. If you're in the right.
Are you running it as a binary?
You have to be in the directory. So if you clone it, you need to go in the directory and install it. Maybe I'll put that on the board. Packages. You might. Sorry, I don't. It might make sense to work together on some of them. I'm sorry? Yeah, so if you do pip install and then I think it's -R and then requirements text, it'll install all those packages. But just like be careful, it's pinned to certain versions. So if you have other things in Python, like it might conflict with those. Yeah, then the virtual environment should be fine. That is a really good point. You don't pick off the web server. You might also need to install Jupyter, and then you can just run Jupyter. Yeah, exactly. If you do like a cond environment, you can there's a whole bunch of different ways to do it.
There's something that makes that much sense.
So quick note: if you go the requirement text route, you might also need to install Jupyter because you need to. I mean, if you want to run the notebook, you're going to need to install Jupyter so you can actually run the notebook. So, quick note: that's not actually in the requirements text. Maybe. Hey, Matt, this is maybe a Matt question. Hey, Matt. Docker login? Does it require Docker login? No. So this in the PyData NYC. You should know this is asking.
Automatically forward. Change the. Yeah. Get Hey, yeah.
So, is everyone totally lost, or is it working for some sample? It's downloading. Okay, so that's a good sign. It's too late. Yeah, we were trying to trim it down. We use a base. We use a base document.
That's a little bit more.
It's already too large.
It's not just and they had like 3,000. So they had it to it. And she
What was the Okay, so it might be sudo apt-get. Either of those commands exist. Are you? No, you're on Mac, right? So brew. I think brew would probably be the way to do it. I think if you brew install Docker, it should be. I mean, you might want to like look it on our website. The last time I installed Docker was a while ago, so it's we're using Python 3. I think it's Python 3.6. Who's first? Okay. The slides are not on the GitHub. No, they're on the Google. I can put the link up there. But it was on the. It's a Google slide. I'll put the link. Oh gosh. I don't think it's. Weird. I can ask. Yeah. Sorry about that. When I run it, it doesn't seem to show that. But I don't know. Maybe it's a version. Now it's okay. Perfect. There we go. A problem solved. Okay. Sorry. I'm going to switch this for 1 second, just to show the slides thing. Should we get going?
Let me just put the Docker start thing command, because I think quite a few people had that problem. Yeah. I can't remember the command line, but
Do you want to do that? Or should I start?
yeah.
What do you think?
Let's make sure everyone's on the same page and we're going to start. I think
This is a it's way a little bit longer.
We're all in this together. We're all in this together.
I can't access it.
Oh, the internet.
Yeah, right.
Oh my god. Okay. So we should probably start moving. If you want to work on it, no, it shouldn't be a problem. Yeah, that's the warning. It's annoying. Okay. So, oops. So do you want to start the part, or do you want to?
I will.
Oh, no, I just got loud.
Let's just go.
This is fun.
Okay, brilliant. So I think everyone's like pretty much almost there. It seems like the internet is good here. So if we do have any troubles once we actually get to the notebooks section, then we can sort that out there. So in this case, we're going to get started on understanding the intuition behind why we might use probabilistic modeling and why even hierarchical modeling would be a good option for us. And so in our world, in the business world, we often get questions from other members of the organization. Maybe they're in the sales department, maybe they're in analytics, and they usually are very high level, and they're business questions like, a salesperson will come to us and say, "Hi, I'm Bob. How can I help you?" This is an example. Ben did this, so he's laughing at me because. So this is an example of maybe if I work at Thrive, like Ben does, and there is a customer that is coming to them, asking them about their business and how they can increase their spend by doing a campaign. And at Thrive, they're experts at this, and they're very informal. And so, an example conversation might go as follows: if I'm the salesperson, "Hi, how can I help you?" And then the customer would be, "I want to run an ad display campaign. How much do I spend?" So here, they're expecting kind of a range of numbers. And it's also open to interpretation, as well as there could be many different factors that go into answering this problem, and you might want to answer this by outputting kind of a range of numbers rather than giving them one specific number. And of course, the salesman might not know specifically what the answer is, but they will ask the data scientist or the data analyst or someone technical that knows the numbers on how they should answer this question. And so, in a perfect world, every salesperson would know the answer, but that's why we have jobs, which is great. So they'll come to us, and then, as the numbers people, we'll try and figure them out, and we'll use our historical knowledge on the industry to try and figure out an answer. And like ideally, we'd want some realistic range that we could give back to the salesperson to say, you should try and sell this customer, depending on where they live or what industry they're in, how much they're willing to spend, kind of a range of numbers that could best or most optimally work for them. And so then the salesperson would come to us as a salesperson, usually in Slack or something, because it's quite informal. So an example would be like, "Oh, I need an estimate for this company Y." The salesperson is telling us on the next campaign, and then we'll come back to them. "Yeah, sure. Give me some few things that I need to know about this company, and these would be the kind of features that would go into my model." And so, and features that would be relevant would be maybe how big of a company are they. If they're a bigger company, maybe they need to have more outreach, and so that could require more spending. Where are they located? Is it in like a big city or a rural area? What industry are they in as well? And so the salesperson would kind of come back to us again and give us the information that we can then put into our models. And then great. Then if we had a traditional like black box based models, then we'd come out with one number, which isn't great. There's no uncertainty there. It's quite opaque, and depending on what kind of model you use, it could be quite difficult to figure out exactly why you got that number. What features were important into that number without doing some diagnostic analysis on top of the model as well. And so then the salesperson would usually come back because they have some industry knowledge and say, "Are you sure? Like, that doesn't sound quite right." And then you'd be like, "Yeah, that's what my model said." So obviously that's not great, and so that's why probabilistic modeling could be an alternative approach to this.
Yeah, just to add to that, like beyond just like getting that range, it's also a conversation, right? Like this salesperson is talking to this customer and like being able to like say like, well, we see for customers like you, here's our range, right? And they might know that off the bat, like the top of their head. Likely they don't. And so something like a probabilistic model where you have that built-in uncertainty, you have that built-in conversation, it's a better, like you have it by nature, it's a little bit better of application of something like this.
Yeah, and another reason that probabilistic models could work better is because they're extremely flexible. You can input whatever priors that you want or might be appropriate, which could then impact the results that you get on the posterior distribution. So this is what we kind of have. We have in our data set, we have customer spend on different marketing products, and that was courtesy of Ben from Thrive5. So this is real data. It has been anonymized.
Right. It's noise data. It's based on real data. It's derived from real data.
And
I have to put that in.
But I think that also points to a good part of probabilistic models as well, is because that you can use generate data from the real data. So this could be great for like an application would be like bootstrapping like different results, as well as if you needed to expand your data set, then this could be a way that you could do it. And so what we have in order to produce, our goal is to get these realistic spends on how much we should advise our salesperson on what they should go back to their client with. So we have customer spends on marketing data products from historical data. We have customer characteristics on what kind of customers typically spend what. And so our aim is to produce this predictive model for estimating that spend range, given some very high-level characteristics. So this could provide a range of predictions which we can then give to our salesperson, and it'll give them the knowledge to make the sale, essentially. And this is one example of using probabilistic modeling for marketing. There are so many applications to it. So there are a couple that are listed here. For example, if you want to look at the lifetime value of a customer, or you wanted to do marketing mix models, which is another application on top of that, as well as you could use it in finance. It's very popular there because there's always some stochastic nature to, say, the values of stocks and bonds, let's say. So these are other alternative applications for this kind of modeling. And so the thing I like about probabilistic modeling is it describes the data that you can observe for the system. So that's again going back to using this model to then create the data that you initially had. And so it uses Bayesian analysis to say kind of if we know probability theory, then and we know some prior distributions of maybe the specific variables, then we can use that into our model. We can use the prior knowledge that we have as industry experts to feed into the model and then make predictions that make sense.
Okay, so show of hands, has anybody worked with probabilistic model-based stuff before? Okay, cool. Oh, good. It's like a good half of people. Great. So you guys can teach me. This is the obligatory Bayes rule. If you haven't seen it before, the basic idea behind Bayes rule, and I've struggled with like kind of wrapping my head around it. The way that I try to understand it is, can we get a better prediction of the world based on the data that we observe? Can we update our predictions based on what we actually observe? And that makes kind of intuitive, natural sense, right? That's just what we do on a daily basis, right? We try and like pick up something that's sharp, and we're like, oh, that's sharp, and now we have data to know to not pick up that thing again, right? We do that sort of as a natural like part of us. And so I think the intuition behind like a probabilistic method or a Bayesian method is like pretty intuitive, even though the stats are super complicated. So the basic idea, I won't like go through the entire like Bayes rule. But the idea is we have, and this might be a better way to think more intuitively about it. We have some data. We have a hypothesis about the action sort of generating that data that we can sort of build into our model. We anticipate, for like in a marketing setting, we anticipate that spend is probably going to have a probably normal distribution, right? Like we have a lot of people that are spending this kind of average ones. We have some people that are spending less. We have some people that are really stellar customers that are spending more. So we can build that knowledge into our model. And then we have how likely the data, we observe this data given our hypothesis about the world, and that's sort of just normalized by probability of observing the data. So Matt sort of already talked about this, but Bayesian models are not new to marketing or generally the field. They've been used in various forms. You could think of, I've seen regularization talked about as basically like a Bayesian kind of update or Bayesian constraint to coefficients. So these things are already kind of in use. These are getting more and more popular. And happy to talk about any of these things. I won't dive too deep into them, but the main power of it is being able to include some prior information about the hypothesis and then get, in the end, sort of a kind of uncertainty estimate around your hypothesis given the data that you observed, updating your predictions based on the observations. So now let's complicate things even more, right? So the idea of a hierarchical model, again, show of hands, has anyone ever worked with like hierarchical modeling or something like that? Man, why are you guys here? You guys don't know all this stuff.
A lot of problems with it.
Yes, and we can talk about, and we will talk about the problems with it for sure. But again, we talked about incorporating some prior information about our belief in the world into this model. Another thing, like a hierarchical structure, is something that we know kind of exists. One of the canonical examples of this is school grades for students in schools. You can imagine in a school district, there are schools, there are teachers, and there's some commonality between students of one teacher, students of one school, schools of one district, things like that. That's a hierarchy, right? And you can build that kind of shape into the model. So the idea is basically to account for these kind of group level differences and allow them to sort of share information between the different groups. A really good example, if you want a great walkthrough for a lot of the stuff that we're going to be doing, is Thomas Wickie's blog. That's the link right there. He's also extended this a lot, and it's just a really great walkthrough. And the example that he uses is one of Andrew Gelman's examples, which is estimating the relationship between having a basement and radon levels in homes. I think it's across a bunch of different counties in Missouri. I believe it's Missouri. And so he goes through three different kind of approaches. There's the non-hierarchical, which is, this will give like a good grounding of like what hierarchy is versus like non-hierarchical. So the typical approach, which is just a pooled model, you're estimating maybe one intercept, one beta for the relationship between having a basement and radon levels. You have like one estimate for each of those parameters. But if you think about that, that doesn't particularly make sense because counties are different a little bit. And maybe basements are less deep or there's higher radon levels by nature in certain counties. There's information at the county level that you're sort of just like kind of glomming together in this pool. That's why it's called pooled. You're just sort of pooling together into this model. And so it's not, it doesn't make particularly the most sense. So maybe what you might go to the far other side, which is making an unpooled model, where you just have completely separate regressions for every county. And also that probably doesn't make sense because even though the counties are somewhat different, there's probably some similarity in the relationship between having a basement and radon levels and radon levels like generally sort of baseline. So you might find the middle point, which is partially pooled model, which is the hierarchical model, or is what we're calling the hierarchical model. And basically that is your estimating a intercept, an alpha, and a beta for each county in this example, for each level in the data. And so you can do a hierarchical model, and it doesn't have to be like a Bayesian hierarchical model, but the thing that sort of makes it a Bayesian hierarchical model or a probabilistic hierarchical model is you're actually imposing sort of a shared prior on these different parameters, which is we've talked about how that's it's sort of useful to have to build in some like knowledge, some institutional knowledge into your model. So all this is basically making a model that better matches the world that you're kind of looking at, the world that your data kind of comes from.
And there's all sorts of hierarchies as well. There's not just region and county level, but you could also think of like maybe like in the calendar month, like the weekend versus weekday, that might have a different outcome on the predictions versus in summer versus in winter. So there's all sorts of hierarchies that you can add into your models that I've have experience with as well. So yeah, you have a question?
Yeah, just in terms of like mapping this to what I'm used to from like OLS, I forgot what the exact words are, but like they kind of have like concept of like this sort of like mixed intercept and varying intercept or whatever, those kind of concepts. Like, can you sort of like map these two together? Because I'm always confused like which one is exactly what and how that relates to like the hierarchical model. Just clarify that, that'd be helpful for me.
Yeah. So from my end, I've heard like a little bit of back and forth on this. So from my understanding, a mixed model, you could also sort of call these mixed models, but the hierarchy part is that there's actually some kind of like hierarchical structure built into it. So for those of you who haven't worked with mixed models are kind of like a similar thing where you allow you estimate sort of different parameters for different, groups, you estimate different parameters for different groups. So it's kind of a similar thing. The hierarchy part is that there's actually like a hierarchical structure that things tend to, and it's not always the case in the hierarchy structure, things tend to nest into each other. Like the example about schools is probably a little bit more intuitive when you're trying to think of hierarchies, because a school district, a school, and a teacher, those things sort of fit into each other a little bit more. There's a lot more to it. I'm glossing over a lot, and there's a lot of like back and forth whether a hierarchical model is just like the same as a mixed model. But you could, I see that the way that they're estimated, the way they're used is pretty similar. So hopefully that answers your question. Yeah, so I won't dig too deep into this, honestly, because the blog post does a much better job. But one of the powerful things about these probabilistic models are some things that we mentioned before. You have some prior knowledge incorporated into the model, and in a hierarchical probabilistic model, you're sharing that knowledge across the different levels, right? These are this visual on the right, I think, just does a really good job of demonstrating the power of a hierarchical model versus sort of like the individual approach, which is the fully unpooled approach, where you have like a separate regression for every different county. And the blue lines are samples from that fully unpooled. The green lines are sampled from the hierarchical model. And you can see that this is the relationship between having a basement and radon levels. I'm ending up going far into this, and I wasn't intending on it. But you can see that the relationship is more consistent across these different counties, and that's even in the presence of like outliers like this one. Even in the presence of in this county, you actually don't have any observations for houses that don't have a basement. And you can see the unpooled model, it's kind of like all over the place. The relationship is not consistent, it's different, it's like exists, sometimes it doesn't exist. With the hierarchical model, it finds this relationship, it's pretty consistent, maybe it shifts a little bit, but because there's information shared across the counties, you can do a little bit better job of like extracting that relationship. In the Thrive Hive context, and I think this applies to a lot of marketing context, our customers' spend varies by things like what product that they're actually buying, what location that they're in. You can imagine that the Northeast is a little bit more expensive to market to than the Midwest. But there's that kind of structure about like there's the high spenders, low spenders, and a bunch of people just like jammed in the middle. That sort of structure is shared across products and shared across different regions. And so building that, sharing that knowledge between the different groups is important. The groups are different, but they have some commonalities between them. Yes, and I just said that. So, yeah, so that's, I think, the power of combining probabilistic thinking with the hierarchical thinking. You want me?
Go to the notebook.
Well, I think maybe we should start. I think we should start with this. I feel like we should start with this. Yeah. Sorry, we'll get to the notebook eventually. Promise. Just give you really just a view of the data. This is derived from Thrive data. We have a few different products. We have 5 different products there. I'll talk a little bit about those products. Happy to go into more detail, but I don't want to like spend all the time just talking about the marketing products. But people who are familiar with kind of marketing products might already recognize these. And then there's region. And so the 2 levels that we're going to be actually using or testing in this hierarchical approach is product level and region level. And the idea is to actually predict spend, right? Like going back to that example, way back, the problem statement, right? They want to know what is the spend for a particular company, for a particular region, for a particular product, and what is the sort of the range of spends we might expect. We want to build that generative model to be able to provide a sort of conversation starter for sales in speaking to these customers. And then we have industry data and size data also included in there. Another piece, right? Yes. Yeah, so this is what I was going to talk about where I'm not going to dive too deep into it, but there's details in the notebook as well. These details are also available in the notebook. But these are the products that we're going to be examining. The thing that we're going to just call out a couple of times is we have some idea based on our own institutional knowledge what we should be seeing from a generative model. And it's sort of shown in this kind of cleaned up box plot over here. Generally, customers that use display advertising campaigns tend to be smaller. They tend to be a little bit less sophisticated customers. If a customer has a display campaign, it tends to be an add-on to something else. So it's usually like a lower spend. For search engine marketing is whenever you like use Google or Bing or something like that, and you see ads pop up, like this is a sponsored ad, that's search engine marketing. Search engine marketing is the thing that's responsible for that. Tends to be more expensive. Tends to be larger clients that use that service. And so we expect to see that SEM is going to be on a larger spend range. Display is probably going to be on the lower spend range. The other ones are sort of distributed within that. Also, I might even call out that search engine optimization is kind of a little bit of a fuzzier service because it includes sometimes like content generation. Sometimes it just includes cleaning up your meta tags and things like that. There's a lot of different services that fall under this umbrella, and they're a lot more custom. So what we actually expect to see is a little bit of like a wide distribution of spends for SEO. So we can talk more about that if you're interested, but I think we should get to the
Fun stuff.
The fun stuff.
It's this one.
Nice. Oh, it's a 13K. Is anyone like are things working in terms of Docker in terms of looking at the notebook pretty well? I don't know. Do you think it makes sense to check?
Yeah, we'll take this time just to verify that everyone's got it working, and if you have any problems, then now would be a good time to like raise your hand and we can figure it out. Otherwise, you can begin to start reading through, examining the data so that we're all on the same page once we get started.
Let's just take a couple of minutes. Just take a couple of minutes.
Yeah, sorry, so this is a little bit hard to, so you want to either use one of these or so you use this, and just use that. Yeah. And remove the parentheses, the right parentheses. And it should work.
Great. Everybody's doing fantastic. Cool. That's good to hear. Yes, that makes sense. Yeah, I don't think. Yes. Yeah. If anybody's okay, I'm sort of jumping ahead. I'm going to just jump ahead because it's so there's this is way jumping ahead. But bear with me. There's this part of the code where you're actually running the model. That takes a little bit of time. If you want to speed it up and make all the statisticians in the room angry at you, just change this argument to chains 1, because that'll just run one sampler. It'll make it about 1/4 the time. But I can talk about what it.
Run in parallel.
Yeah, but it's. But yeah, they run in parallel. Yeah.
If you just do they by default?
It's more.
If you have enough processors, you should be fine.
I think I think you have to like specify that they should run in parallel.
By
I don't
default, think times 2 runs 4,000.
Do they? Okay. Well, it takes longer, right? Like so, this is this goes up to it should be 4,000. It goes up to 16,000 or 1,600. Sorry.
Your output there says 4 chains and 2 jobs, so clearly it's sort of parallel, but not all 4. It's
Yeah, I mean, if you guys have worked with PyMC and like parallelizing before, feel free to like switch and tweak those. That's a really quick fix for making it run a little faster. Also, if you want to make it run even faster and have terrible results, you can reduce the numbers here, but terrible results.
I don't know if you guys sort of what the layout of the rest of the session is, but like, are you guys gonna go through like how you pick the prior?
Yes.
The key?
Yes. Yeah, sorry. So I was jumping ahead because if you want to run the models, start running the models now, that's probably makes sense. Because if you start running them when we actually get to them, it might be the end of the session, you're still going to be running them. But we have the results here, right? Yeah. So we can go through them and go through what you'll see. But yeah, let's go back.
What's the runtime for the whole notebook?
I don't know off the top of my head. But the chains are the sampler is the thing that takes the most time, by far. I mean, okay. Yeah, let's just. I don't know. So the data that you're going to load in, that's from the repo or from the Docker file. This is sort of a key to what those variables sort of mean. I don't know if there's anything particularly. Do people have any questions about that? I mean, that's just sort of documentation. Cool, great. I'm just going to go through it. So this is the same sort of descriptives that I had before. It might be a little bit different from what I showed up there because this is a sample or a generated sample of the data. Oh, I should mention, this is based on real data, which means it's not like we didn't sanitize it or anything. That's why it's. I think that makes it a little bit more interesting because, like, I feel like a lot of the tutorials I've seen use like a constructed or sanitized data set. This is like based on real data, in that it's like a noised version of real data. So that's.
So that was.
I thought that was exciting. Okay, so we're going to try 3 different things, 3 different models here. We have the pooled model, we have the product level model, and then we're going to have a product and region level model. And the level is basically we're just going to estimate an a alpha for each of those levels. We're not going to include actually estimating a beta for each of those levels. This is just like a kind of first cut analysis. Pooled model sort of looks like what we kind of expect. I just split out the different betas just so it's easier to like read in the end. You could basically this is essentially equivalent to just having a normal prior on all of the different betas. Sorry, I'm jumping around a little bit, but we're using unit Gaussian priors for basically everything. Why did we choose that? Because it's simpler. There's a lot of different thought. And did anyone go to the Bayesian, either the beginner or master class during this? Yeah, so that workflow is probably the workflow that you want to apply. A lot of thinking about what is the prior information that you're going to include. But if your interest is to try and run the model and see that, like, and test out these methods and see what the results that you kind of get, this is a pretty uninformative prior that will behave pretty well in sampling. So basically we're putting uninformative priors on here. And you'll see how that sort of shakes out actually in the next parts.
So for the, why did you pick a half quotient and not a half normal?
It's to be positive.
Well, the half normal.
Yeah, the half normal is all, yeah. It's something that I've seen used. There wasn't a lot of thought that with a
Half quotient uses fatter tails, so it allows you to have large supers if you want it.
yeah. So maybe yeah. So it performed well when I first ran it. So I was just like okay.
Very good.
So right, this is going to be focused on like an implementation. We'll actually get as a teaser toward the end. We'll get to like a possible method for like turning this into a prediction method. So focus is on like getting results that getting through a full workflow. Okay, cool. So you see in the pooled model, we just have one intercept for everything. In the product level, now we have a product level intercept, which is this product alphas. We also impose some things that are sometimes referred to as hyperpriors. They're basically, we replace, where we have up here, we've hard-coded sort of the mean and the standard deviation to be 0 and 1. Here we have them as random variables that are also estimated by the model. That's a little bit more in line with how these models are usually done. Just hard-coding like a mu and a standard deviation is usually not the best practice. But we'll actually see how that a little bit can complicate things. And then product and region is a similar thing, where we just have an alpha for product and an alpha for region. Now you see all these like all this math, well, kind of math, and you're like, how do we actually turn this into something that can be processed, that can be run, that's actually the model that's in the that actually gets sampled from, and the answer is PyMC is great, and basically you can write almost exactly what you have up there into the PyMC context. So the way PyMC works is you initialize a model instance, and then you basically specify all of the different random variables and their priors and whatever other information you want to include. Not included in here, you can also have it do some calculations, like what is the difference in means or something like that. Do some other sort of any kind of like mathematical kind of derivation you want it to do. It can do in the model context, and then it'll output that as a result of the model. And what else? Yeah, and so the thing that we're trying to predict here is spend, and we feed it the observed data. So this is when we go back, if you think all the way back to that the sort of Bayesian framework, this is the data part that we're giving the model. And then we just put it into a dictionary. So that's like, this sort of is how PyMC works. You initialize a model context, and then you can define all the random variables. And that's what you need to set up the model structure itself. And then comes the fun part, and that's talking about how the sampler works. Do you want to go back to the slides? Talk about that part.
Yeah. Actually, yeah.
So I won't dive too deep into the methods, also because we're running a little bit short on time. But basically, how you actually get the posterior, which is the distribution that you sort of want out of in that Bayesian framework, right? The thing that was the probability of the hypothesis given the observations that you have, is through a sampling process called Markov chain Monte Carlo, broken down right there. There's a couple of different algorithms for doing that. The basic idea is the algorithm is going to propose a new value for that parameter, and it's either going to accept it or reject it based on whether it increases the likelihood of the data being observed, and sometimes accept even ones that decrease the likelihood with some probability, if that sort of makes sense. I love this visualization. This GitHub page has a lot of really cool visualizations and takes you through a lot of the algorithms. Definitely recommend it if you want to dig a little bit further into the algorithms. The way, the sort of default that gets assigned by PyMC for our sampler is called the no U-turn sampler. It is based on some physics concepts that I very, very loosely can grasp, but the idea is instead of like each individual like proposing a point, thinking about it, proposing a point, it actually sends this sampler sort of into a probability space, and it takes a bunch of samples and like sort of loses its energy. The way I've heard it intuitively explained is like a puck going through like a pit like this, and so you send it down here. It can move very quickly through these areas of high probability and can't move up these walls very much, and so it loses energy and sort of stops its motion. And so that tends to speed up the process versus the Metropolis-Hastings method. The end result being that you have a sampler that is like pulling from this posterior distribution that you're trying to estimate, and it'll sort of like move through these different values as it sort of samples. Does that make sense? I had a little hand wave my way through that, but cool. I'm gonna take that as a yes, that makes total sense. We should go back to that. So what PyMC gives you as one of their trace plots, or what's called a trace plot, is this really kind of interesting visual of the sampling process. So remember what I was saying about it like moves from point to point? This is what that kind of looks like. It moved here, and like what you typically want to see is that it's doing a good job of exploring the space. It's not getting stuck in any values particularly. I can show you, if we have time, what it looks like when it failed miserably. But this actually looks pretty good, pretty reasonable. And then you also get, on the left here, these are the posteriors. The posteriors for those different product betas, posteriors for size, and for region here. The acceptance probability error, I have some details about what those errors sort of mean. Very quickly, there's these numbers up here. Sorry, and I said I was going to actually explain these. So there's the number of traces, the number of tuning steps, and the number of chains. Those are not all the options that are available to you in the sampler, but these ones are sort of the things that are required. The tuning steps is basically the sampler is going to run for this many samples, and that's going to sort of tune the parameters of the rest of the sampling. So it's going to run 1,000 times and sort of tune a number of different parameters. Yeah.
What's it tuning? What kind of parameters is it?
So there's a bunch of different parameters. I don't have off the top of my head all of them. The one that's relevant to this error that we're getting here is it tunes how ambitious the sampler is going to be. Like if the step size is going to be huge or the step size is going to be little tiny. If it's tiny, then it's more likely to accept the proposal of the new step, but it's going to take a long time to get any results that are good or reasonable. If it jumps, it's going to reject a lot more, but it probably will explore the space a little bit more quickly. Does that sort of make sense? That's the one that's relevant to that. There's a ton of other things that go into the tuning things, and I definitely could not tell you everything.
Is that the warm-up period, like where you just kind of like get the parameters?
Yeah, so I don't know. I haven't heard warm-up period before.
Not just the warm-up period. The other method is the warm-up period.
Yeah.
Burn-in?
Yeah, I've heard it called burn-in before.
Right.
Yeah, I've heard it called burn-in before. But yeah, the trace is the actual number of samples post the tuning that it's going to run. The chains is how many samplers it's going to run. The default, I think, is 4 that it runs. But by forcing it to do 1, it just goes a little bit faster. I can hear everybody's computer just struggling right now. So
So does it run 3,000 samples per chain, or just 4 chains in total?
so it's going to be 4,000. So this one ran with 4, so it's 16,000 samples.
Oh, yeah.
So it's like 4, yeah. So it takes some time. This stuff takes a little bit of time. Yeah, you can speed it up, but like speeding it up also, you get results can be a little bit volatile. So the acceptance probability. The target is the thing that's tuned during the tuning step, and so the actual number of proposed jumps was like the percentage of them was 80% of them were accepted, and it was looking for about 90%. So you can change that value as well. You can also specify what the acceptance probability is going to be with the same sort of caveats, right? If you accept more of them, it might, if you accept more of them, it's going to do some more ambitious moves. If you accept less of them, it's going to sort of be a little bit more conservative. And there's caveats to all those things that are a whole set of blog posts by smarter people than me.
Is there a general rule of thumb on what the acceptance probability should be?
So I don't usually pre-specify that. I usually use the tuning thing. And so what it recommends, where you have more tuning steps, I would probably do that. But again, there's a time trade-off, right? Like say if you want to get to some results, you might want to try and just, a lot of the Bayesians that I've heard talk tend to be more focused, less focused on these like single metrics, and more focused on does this model look like what we expect, right? Have we created a generative model of the universe, right? So that's the thing that I think diagnostics like just kind of a visual look, a qualitative look from you and from people that are involved in the process might be better than actual just single metrics. Let's see. I don't know if there's, yeah, I don't know if there's much. I'm not going to talk too much about these. So this is the baseline model, right? So yeah, we're let's move on a little bit. So now we're going to talk about the product level, where we have these product level alphas and we have these hyperpriors specified. Again, the sampler looks pretty reasonable. Like it looks like it's exploring the space pretty well. It doesn't look like it gets stuck in any particular region. Here's where I want to actually look at the posteriors for these product alphas. I don't have it labeled here, unfortunately, but this is the posterior for search engine marketing. And these two are email and display. This is sort of, remember we had talked about before that display tends to be a smaller spend product. SEM tends to be a higher spend product. This is that's a really a simplification of things, but this suggests that we're not completely way off of what we might expect. The posteriors don't completely not match with the reality of the situation that we're dealing with.
So, for somebody who doesn't understand this, right? This is supposed to be intuitive to somebody who knows it. Can you put a little more color on why this actually looks intuitive in terms of this is what we expect? Because I see, 4, 5 Gaussian curves, but what do you mean it looks like we expect is one higher, the other is lower?
That's really it. I'm giving a very simple read on this, and there's a lot. We're gonna dig a little bit into the actual what the predictions actually look like and how those match with the reality. But literally, this is a good time to stop and check and see that the posteriors that you're estimating. And so these posteriors, it's a good point. These posteriors particularly are the intercept for the product level, right? This is where it kind of starts, right? If all other things are set to 0, this is the anticipated spend, or this is the range of anticipated spends. So you'd expect that display and also email, which is also low spend, to be lower than SEM, and you'd expect those curves to be pretty far apart from each other.
So your units on the x-axis, you're saying, is a function of spend.
Yeah, sorry. So this is log This is log dollar sped. Yeah, so the x-axes are not labeled here. The trace plot doesn't naturally label them, but you can extract the different parts of the plot and use them in any way that you.
Are there any other units on the axes that we should be considering? What are the units list? The alphas, the betas, the mu alpha, mu beta. Is that just supposed to be about 0?
Yeah. Yeah, I mean, it's the same axis across the x-axis is the same across the board, across all these things.
So they're all log dollar spend.
Yeah. Sorry, you're right. No, you're absolutely right. No, right. So these mu alpha and the mu beta are not. Because those are the hyperpriors. I'm sorry about that. No, it's a really good question, and thanks for stopping me at that point. But those are the hyperpriors that you're putting on the alpha and the beta parameters. So, gosh, I don't know what you'd label those x-axes as. Just probably, I don't know, values.
Yeah, they're the.
Expected value of the distribution.
Yeah. That makes sense, right? The expected, right? Yeah. Cool.
Distribution of that average.
Yeah, I like that. Okay. Yeah, so it's expected, right? It's the expected value of the different distributions, so the alphas and the betas. So remember, we were hard coding it in the pooled model as 0 and 1. So now we have a distribution of what those mu's and sigmas kind of look like. Cool. Okay, so not anything particularly else to call out. This is then the hierarchical product and region. Now, so here's where I ended up actually removing the hyperpriors on the region, and we'll talk about that if we have time. If you try and run it with those, you'll see the sampler leads to some wacky results, and again, just it's not particularly good practice to just strip them out and force it to be at these different values. It's better to actually examine why the sampler is getting stuck in certain regions and why the sampler is giving you weird results. But this is to sort of get to an endpoint that we can use. Did you have a question?
Yeah, so just on the previous one, maybe we just want to move on, but for region, this was region betas, not product. Region betas. Okay, never mind.
Okay. Yeah. What else? Yeah. So okay. Yeah. So I wanted to also point out these are kind of interesting. So. So on both of these, and I'll just mention again, these two scales are log dollars. So this is the product alphas that we remember from the last one. We saw a little bit more of a spread. These seems to be a little bit more tighter together. And here's our region alphas. So does anybody see anything problematic about this? Can anybody tell me that there's how we might interpret this?
I mean, it essentially means that in this case, every region is spending the same amount approximately, which seems way the hell off base.
Well, so yeah, I mean, so that's one way of interpreting it. I interpret it as region doesn't provide particularly useful information. That's how I read it, right? And that makes, I think, intuitive sense because region these are the four census regions. That's way too high level, right? If people have worked with marketing data or any data that has a sort of geographical nature to it before, you probably use zip code level stuff, or you probably even extract from zip code what is the population density, what is the urbanness of the area. Those are the sort of things that you're a little bit more focused on rather than what region do they fall into. So how I interpret this is that region is not informative. and I think that's why the sampler kind of has problems with it.
Why do you say the sampler has problems with it? Just because it's all over the place?
So I think this trace is, I mean, you know, it seems like it gets stuck in certain regions here, but I can show you what it looks like when you include the hyperpriors, right? And it's then how I interpret why it starts having a hard time is it's trying to fit a very complex model on no information. And so then the sampler just doesn't have anywhere to go, or it's not easy for it to choose somewhere to go.
So for the product betas, the trace looks pretty narrow. Do you think that means it's not exploring the space?
It's a good question. From what I've seen, that's okay, right? Because ostensibly it should be if there's some evidence that it should be going off in a certain direction, just to start going off in that direction. It may just be that is the space that the number of values are the most likely values that parameter is going to take. I've seen a number of these different trace plots, and having a narrow band is not particularly a problem. It might just be that the distribution is narrower, right? But it's a good question, and like, I think things will start making a little bit more sense if we get to the actual predictions. Yeah, well, so the evaluation metrics will go over, when does this end? Oh, we have plenty of time. Haha. Okay, so maybe we should go back to the slides. This stuff. Okay, so we looked qualitatively, and as I said, a lot of these things from my experience, it's sometimes it's just a matter of looking at the generative model that you've assembled and seeing like how it actually matches the world. But there are metrics that you can apply. There's a whole suite of metrics that you can apply to see how good your model's doing at sort of fitting the world. One of the ones that I've seen used and uses a sort of Bayesian intuition for forming its conclusions is the WAIC, which works a little bit like the AIC that people have worked with, where a lower number is the thing that you want to see out of it. Basically, very high level, that the there's a lot more information in these sources, by the way. I'd highly recommend if you want to dig into these. The Pyronen is actually a survey of Bayesian model evaluation metrics, and I thought actually pretty accessible. So I recommend it. But basically, it's the likelihood of each observation penalized by the average variance of the data. So when you have very small samples, obviously the variance becomes very large. And basically, that's kind of stand-in for typical machine learning is like cross-validation. This is like you're kind of like leaving one out and seeing how likely that point is based on the model that you've sort of set up here. And PyMC has WAIC sort of built in, and it gives you a couple of other metrics as well. So you have the WAIC, you have the penalized WAIC, which is just penalized by the number of parameters that you're trying to estimate, which is also pretty informative. Yeah, and so we can actually run that in the notebook. So what we get out of it is this WAIC, the PWAIC. The DWAIC is the difference from the lowest WAIC. So you see here actually the pooled model has the lowest WAIC, but like the difference is not huge, and I kind of like the idea of including something that splits out the different products, because it's based on experience. Like the products are different enough that having a single and just that probably doesn't make the most sense. And then you can see our product region model has the highest WAIC. So it probably makes sense to, and just looking at the data, like there's two things, right? We have these metrics that come down, we have our observations, and those things together tell us that maybe that model is probably not the model we want to run. But you can imagine in that principled Bayesian workflow that we would, go back, try a bunch of different types of models, try different priors, see what the results are, try and run these metrics, and then sort of choose to go forward with a certain model into the actual predictions, which is the exciting part that we're about to dive into here. So maybe go back to we should go back to the slides. Yeah. So, so the difference is, and we sort of talked, or Matt talked about this at the beginning, what we're kind of getting out as a prediction is not like a point estimate for each observation. We're not just saying like, here's the value. It was, what was it? You had like 12,000 or something like that, or?
Yeah, 12,000 or something. That might be an example of your output from a black box model. But for the Bayesian approach, obviously you get a probability distribution, which can be a lot more intuitive and interpretative, and you can then give that to another member of your organization and they can do what they want with it. And it gives them an uncertainty level as well as a way to kind of just manage their expectations on having one number, which puts a lot of impetus on kind of that result.
Yeah. Yeah, and so what you get out of the Bayesian workflow is you get this predictive distribution versus this like prediction, and then you can sample from that predictive distribution, right? That predictive distribution is kind of that generative model that we're sort of, or I guess the model is a generative model, but that predictive distribution is the sort of result of that generative distribution. These are the actual like expected values of spend for every customer, every observation that's in the sample. So you can sample from that distribution, and it's powerful to actually like look at that and compare it to like the actual real world distribution, which we'll do in the.
Sorry guys, just on the predictions. So just to, this one thing that sort of always confuses me a little bit about stuff. So I do a whole bunch of sampling to like train the model, and then I need to do even more sampling to make predictions.
So it's not, you're not sampling in the same, you're not sampling in the same way, right? Your model that you've derived from that sampling process enables you to create this predictive distribution, and then you're just pulling from that predictive distribution, and you're sampling from that predictive distribution that you've created. Right, you're not actually changing the internal values of the model. The model is now designed, and now you're pulling out the predictions.
So there's no MCMC or any of that stuff here. There's almost just like a random number generator, much like you would randomly sample from a normal distribution.
Yeah, that's an interesting way of thinking about it. Yeah, it's not like a random number generator, right? Because ostensibly you've made a good model. But yes, right, you're pulling from it. This sort of stays how it is, and it'll vary like what you'll pull out of it because it's a distribution, because you're sampling from the distribution. But that distribution should sort of stay like that distribution.
And so when I think about there's uncertainty in my parameters, because I sort of have like two sources of uncertainty, and maybe I guess the length, or like, because I have like some distribution in my input data that I guess it's reflected in the parameters that I estimate. And so that defines sort of the parameters that get estimated. And then when I sample from this, because this doesn't look at the input data at all, right? It just kind of says like, hey, I've trained this model that has some sort of variance. It doesn't think about the input data. It just kind of Because I'm sometimes wondering, like, you have uncertainty in your input data and you have uncertainty in the parameters, and I always sort of thought like they're
Well, your
counting, but I guess like yeah, sort of.
Yeah, so how it's been phrased, and I really don't want to get this wrong, the data is considered in a Bayesian model fixed, right? It's not considered to be like random, like the frequentist approaches.
Yes.
Right, the parameters are fixed and the data is random. And it's the reverse in probabilistic models, right? So this actually is treating the data as fixed.
Yeah. Okay. Yeah.
Hopefully that answers the question. I think I got that arrangement right. Yeah, so posterior predictive checks are really exciting, I think. Yeah, maybe we can, I think it might make sense to just like show a little bit. Like this is how you basically sample from the posterior predictive, posterior prediction. And then you basically get, so I specified I want 1,000 samples from it. So you get an array back that's 1,000 samples, and then it's the n, the number of observations that's in your data. So you have basically 1,000 data sets that it samples from this posterior, predictive posterior prediction. And then I just want to map some of these. I just take like a sort of random sample of some of these like 1,000 samples that I've pulled, and sort of map that onto the actual distribution. And I kind of obfuscated this away, right? When I showed you the box plot, that these distributions are 100% not like, well, not 100%, right? A lot of these distributions are not normal, right? Or not like, you know, like simple Gaussian distributions. And you can see the dark lines I should specify. The dark lines here are the actual distributions, and the light lines are the samples from the posterior predictive distribution. And so you can see for things like SEM and SEO, maybe our posterior predictive distribution is doing a good job. Our model is putting predictions that are fairly reasonable. They seem to map onto the actual distribution in somewhat reasonable way. But then if we start looking at display, email, and social ads, there's obviously a difference there, right? We've enforced, and this is going back to the problems that I kind of alluded to before. We sort of enforced that the output is going to be this normal distribution, and the actual reality is it's not a normal distribution, and so it's trying to the output it's going to give you is a normal distribution that doesn't particularly map onto the reality of the situation. So you can see a lot of these things have these like bimodal kind of structures, and that goes back to even within these different products that I've sort of specified, there are products within them. Right? There are products that are cheaper, there are products that are more expensive. And so having these 5 products is sort of, I've obfuscated away some of the interesting information about the products, right? So maybe it makes sense that it seems like there's pretty clearly 2 distinct products in display. And again, this comes from your consulting with the actual stakeholders. You consulting with the people that are actually generating this data, so you can make a model that is the generative model of the data. But so generally, I see from what I see here is that the mean of the posterior predictive distribution doesn't seem to be way far off from the actual values, so maybe we can output some sensible predictions from this model. Yes. So I'm going to do something that to sort of just have a nice, like, easily usable metric. I want to test. So the thing that I actually want to test is I want to test, are we going to output from this model something that a salesperson is going to be like, that's way wrong, right? Like that's what I kind of want to test. And so I'm going to do something that most Bayesian statisticians will tell you is totally wrong, but actually just do like a difference in means test, and that's just the t-test that I'm throwing at this. Again, not the best approach, not in line with actually testing a fit of a Bayesian, of a probabilistic model, but if you're looking to put something into production, the thing that you're focused on is not giving people wildly inaccurate predictions, right? And so from that standpoint, I feel like this approach makes some amount of sense. But again, if people who have went to that Bayesian master class, he specifically said that like looking at these differences in means is not the way to evaluate the fit of your model to the real world generated process. So we're going to do it anyway. And so we just take our samples from the posterior predictive distribution. We take the average t-statistic, we take the average p-value to see like how often essentially these means are different enough from each other that we should be concerned. And you can see I break it down again by product because I just think that's an interesting way of looking at it. And sort of as we'd expect, SEM and SEO, they seem to be, it seems like the posterior predictive distribution fits a little bit better onto those than it does onto something like display, and we saw that just on the visual observation of the distributions. So now, another fun part. I guess it's all fun parts. So maybe let's just jump back to the slides real quick. So, actually, sorry. Well, whatever. So one of the things that we wanted to do here, right, like in the actual thing that we use in production, we wanted to have some kind of production pipeline that a salesperson could go in, plug in that, that situation that we outlined before. They could plug in, hey, I have a customer, they are a cafe, they are in the Northeast, they want a display advertising campaign. Where should I start? Like, what is the budget range that seems realistic for them? And we want to provide that to them without having to just have a Slack back and forth conversation. And so the solution that we sort of went with was just like a sort of Flask application that's just kind of internal facing. And basically we will retrain this model. We will save both the model and these variables in the form of Theano shared variables to S3. And then we're able to pull that on request and output basically a range of predictions for that particular customer in that particular region for that particular product. And so I'll show you a little bit how to use that. The power behind this really is, so PyMC is built on Theano for now. And Theano has a shared variables module, which allows you to sort of replace the values that are in the computation graph, like whenever you kind of feel like. And so you can do it on request, right? As a request comes in, replace those values, and then the posterior predictive distribution samples will be for those values that you've sort of plugged into the shared variable structure. Does that kind of make sense? And so we can show it in the notebook itself. So I just have, I just make a copy of the shared variables just to maintain it. I have just a function for like reading a query JSON and converting it to dollars in a very simple transformation kind of way. So I mock this query, right? So this is a display customer, they're in the Northeast, they are, full service restaurant. And then I run it for display and then I run it for SEM. And then here's the results. Again, apology that this is not labeled, but this is the actual dollars, right? Because we just did a simple transformation. And so this is the SEM spend range, here's the display spend range. You can see that they're very, very, very different. And the thing that I wanted to just pull out of that, like, here's sort of going all the way back to the beginning, right? Here's the answer that you sort of were looking to give your salesperson, right? Here's the conversation starter. Like, oh, okay, you're this cafe, you're in the Northeast. Well, we see that customers like you tend to spend, maybe around $1,500 on a campaign. You know, there can be like 1,500 to 2,000. Like, it gives them a little bit more power to have a conversation around the numbers that are being generated rather than just like a point estimate. So that's just one way of doing this, not necessarily like this is the best way to deliver on the promises of like a probabilistic model, but this is the way that we sort of use it. And we sort of work with sales to improve these models and get better estimates. Yeah. So many questions. Well, it's kind of going back first.
So how does that distribution would help a customer decide how much to spend?
I mean, I think that's a better question for sales. But how I've heard salespeople like use this is they're like, well, we see customers like you spending like between this and this, right? They can pick. They can understand a distribution. They can understand that like this is high. There's like more people here, less people here, and so they can frame the conversation how they want, right? Like most people sit around here, they might ignore the lower spend people, and then it's like, but we see people spend up to this amount, right? And we can add more information. We can add like temporal information in there. Say you're doing a campaign in summer versus fall and things like that. We could do another model like that.
So,
sorry, I'm first.
Just real quick, what's the round trip time for one prediction? And do you return a histogram to your?
Yeah. So I glossed over that. We actually store all the predictions prior, right? We don't actually run the model predictions, but it takes no time, right? But we wanted to store the prediction just so we don't have to load the model. Does that make sense? Like, there's two ways you can do it. If anyone went to, I think it was one of the ShopRunner presentations, they talked about like two different ways that you can use your Flask apps in production, and it's either pre-compute or have the model like travel with your app. And so we had the model travel with the app, and then we just sort of decided to switch to like, we're going to pre-compute this range every time we rerun this model, and have the application pull on that.
So you're pre-computing every possibility?
Yeah, there's not, I mean, in this situation, there's not a huge amount of possibilities, right? There's all of the different industries that we have, there's all the different regions, there's all the different products. It's not that many. We're dealing with categorical type information. Okay, sorry.
I was just curious, like, what are your salesmen selling? Are they just trying to help the customer get a handle on approximately how much they can spend,
Yep.
or are they trying to get the customer to spend a certain amount of money?
It's both, right? Like, they might want to steer them towards a certain direction if they know something about it, or they know they want to focus on something. But a lot of like I said, a lot of our customers are new to digital marketing. They don't know what is the right spend, and so this is a good conversation starter.
For negotiation, you can start with a highball number of like 3,000 at the upper bound. You're not going to go, however the negotiation goes, you're not going to go below 1,000 because like it's just way out of the bounds.
Right, and they have certain constraints that are not built into here, right? Like there's certain amounts that they can't spend, and the model doesn't know those yet, right? But we can build those in. Yeah, I think, should I? Okay.
So in this case, it seems like the hierarchical model didn't actually improve. In real life, do you see it actually performing better than the pooled model?
If you run the pooled model and do the same sort of posterior predictive checks, it looks worse. And that's just like a qualitative sort of top-down examination. So I think the hierarchical model did do better, but there's a ton of information that we're encoding not particularly much information into the product, right? We know that the product spend looks like a certain shape, or we know something about the shape, and we can code that in to this model. This is a very, 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 very simple version of what we should be doing. Cool. All right. Well, if you guys want to come up, we'll chat after or out of the room or something like that. Thanks a lot. Thank you.